We are back to many electron atoms at last, but then the detour that we took was long, perhaps meandering, but fruitful because it has taught us two most important approximation techniques of quantum mechanics, variation method and perturbation method. So, today what we will do is, since we have talked about many electron atoms perhaps maybe 2 weeks ago or something, we will just do a quick recap of what we have done. Since we have done many perturbation theoretic calculations, we are going to present the perturbation theory for helium, but we will not work out every step, but we will just show you the results and hopefully that will convince you that perturbation theory is a good way to go for systems like helium. In the next module, we are going to talk about variation method and perhaps we will also mention certain things that we cannot avoid mentioning anymore, we should do it now. But before that, I hope we have not forgotten that for many electron atoms, this is how we wrote the Hamiltonian. In a concise form, the Hamiltonian of many electron atom is essentially a sum of n number of 1 electron Hamiltonians plus a sum of n number of, not n number, a sum of this NC2 essentially number of electron repulsions. We are taking pairwise repulsions here. Okay. So, there are n number of electrons, so each will repel the other. So, number of combinations of those electrons that we could take, the combinations of 2 that we could take is NC2. So, basically that number of terms will be there for this electron potential, electron repulsion, and what we have learned, well, 2 weeks ago, is that this electron repulsion cannot be ignored. Remember, to start with we had tried to wish it away and learned very soon that you cannot do that. So, then what we said was, let us build this electron repulsion term into the nuclear charge itself. Let us talk about something called effective nuclear charge, which is the actual nuclear charge, well, theoretical nuclear charge minus a shielding constant, because the effect of electrons repelling each other, you can think, is like one electron shielding the other one from the attractive potential of the nucleus. So, we said that instead of having 3 kinds, well, 2 kinds of terms here, we might as well build this electron repulsion into this Z, and then things become a little easier to handle, because this becomes a Hamiltonian and the wave function also has to be changed, and that becomes a wave function that involves not Z but Z effective. Alright. With that, we had shown you a calculation in which this shielding constant, incorporating shielding constant, we get the value of ionization potential or value of the energy of the potential of a helium atom, which is more or less close to the actual experimental value. Okay. So, that is what we had got. And then at that time we had said there are methods like perturbation theory and variational method that help us estimate Z effective. So, that time we had made a tryst with destiny, and now we must redeem our pledge. We must see how perturbation theory and variational method can help us formulate the problem of many electron atoms in a suitable manner. Okay. And the other thing that we had discussed, remember, is spin angular momentum. This I do not know why again I forgot to move this a little bit, but anyway we talked about spin angular momentum, and the reason why I bring it up once again, even though you are familiar with this term, is that please do not forget that spin quantum number of electron is half, ms is plus half and minus half. Okay. So, spin angular momentum S is given by h cross into square root of s into s plus 1, where s is the spin quantum number, and z component of that angular momentum is given by your Sz, which is ms multiplied by h cross. When we say plus half minus half, we are talking about ms and not about s. And then we know that we have to talk about spin orbitals. we have to take the special part of the wave functions, the orbitals, and multiply them by spin part whenever we talk about many electron systems, because here spin is going to play a vital role. And how it plays a vital role was manifested when we tried to think how many different spin orbitals we can write. For a simple 2 electron system, we can write alpha 1 alpha 2 beta 1 beta 2. Both the electrons have up spin, both the electrons have down spin, no problem, you can even see it experimentally. But we cannot write alpha 1 beta 2 or beta 1 alpha 2, because you do not know whether it is 1 or 2 that has alpha spin. You do not know whether it is 2 or 1 that has beta spin. So, you must take linear combinations, and linear combinations can be taken in 2 ways: symmetric with respect to exchange and antisymmetric with respect to exchange. Symmetric or antisymmetric with respect to the exchange operator. So, we see that we can, when we talk about spin orbitals, we can have symmetric and antisymmetric spin orbitals with respect to exchange, and that takes us to the 6th postulate of quantum mechanics, which says that for identical fermions like electrons, the total wave function must be antisymmetric with respect to interchange of all the coordinates. Okay. And that essentially, as we learned, led to Pauli exclusion principle, which said that the ms value must be different, and incorporating that we learned how to write this many electron atom wave function very conveniently in the form of a Slater determinant. The good thing about Slater determinant is that we just exchange the 2 rows or columns, there is a change in sign which implies that it is antisymmetric, and also if any 2 rows and columns are same, then the determinant is 0, which ensures that no 2 electrons can occupy the same spin orbital. It is as simple as that. So, this is the point where we stopped talking about many electron atom and started talking about your approximation methods. Okay. Well, this is the point after showing the Slater determinant for an n electron atom, we did not stop at 2 or 3. Now, before going forward and presenting the perturbation theoretical treatment of helium ground state, let me just introduce atomic units, which I am sure many of you must be familiar with. In the subsequent discussion, most of the time we are going to use atomic units or natural units. So, that helps us a little bit, because you do not have to write complicated expressions, our expressions all become smaller. But the danger of that is that you must not forget that there are lots of 1's in there, and you should not forget which one is 1. What am I talking about here? This is what I am talking about. For mass, the unit I use is not kg or gram or pound or anything. I use the unit, I use mass of an electron as unit, right. What is the mass of an electron? I do not even remember, very very small quantity in gram. So, that much of gram I say is 1 unit of mass, 1 atomic unit of mass. So, wherever mass is there in any expression, I will get 1. So, expression will become simple, but I must not forget that mass is actually there. Okay. This actually reminds me of this question that we often ask: activity and activity coefficient. Activity has no unit, activity coefficient has no unit, but concentration has unit. So, what is the fallacy here? How can you have something with a unit multiplied by something that does not have any unit, giving you something that does not have any unit? Actually, that also is a ratio. This is essentially a ratio. When I say, when I use atomic units, what I am doing essentially is that I am dividing the mass of any object that I am handling by the mass of an electron and representing it in units of electronic mass. Similarly, charge is represented as units of electronic charge. Charge of an electron is said to be 1 in atomic unit. Angular momentum is written in terms of h cross, most important. We do not stop writing all those h crosses that we have been writing. So, if you ask what is the spin angular momentum, we simply say root over s into s plus 1. Okay. And similarly, z component of angular momentum we simply say ms. We do not even write that h cross, because we are setting h cross to be 1 atomic unit. Permittivity, we stop writing that annoying 4 pi epsilon 0, we set that to be 1 for now. Length is represented in terms of Bohr radius. I have not written the expression, but we know what Bohr radius is. Electric potential is written in terms of potential of an electron, sorry for the typo, an electron in first Bohr orbit. Magnetic moment is written in terms of Bohr magneton, we are not really using it right now, and energy, very important, is written in terms of Hartree. So, Hartree is twice the ionization energy of atomic hydrogen, and if you remember the ionization energy of atomic hydrogen is 13.6, right, actually 13.605. So, twice that is 27.21 electron volt. So, 1 Hartree is 27.21 electron volt. So, that is a large number for atomic systems, a significant number. So, when we talk about atomic unit, energy in atomic unit, you see that we often go into many decimal places, and you might wonder what is going on, why are you writing 5, 6, 7 decimal places? Because when we convert that to electron volt, we get a number that would perhaps differ in so many decimal places of atomic unit. With that background and knowing the Hamiltonian for helium atom, what is the Hamiltonian for helium atom? It is minus h cross square by 2m del 1 square minus z square by 4 pi epsilon 0 r1, that is the Hamiltonian for electron number 1. For number 2 it is minus h cross square by 2m del square minus z square by 4 pi epsilon 0 r2. And what is this sore finger sticking out? Z square by 4 pi epsilon 0 r12, that is your electron repulsion term, because of which we have had to study all these new things over the last couple of weeks. So, what I will do is I will take this, start from this Hamiltonian for helium atom, and I will write it in atomic units. What will happen? All the h cross square will become 1, all the m's will become 1, because here m is mass of an electron. So, the first term and the second term, what will they become? Minus del 1 square minus del 2 square. What will the third term become? E is said to be 1, 4 pi epsilon 0 1. So, you are left with minus z by r1. Similarly, in the fourth term you are left with minus z by r2. But do not forget that E square is there, 4 pi epsilon 0 is there. It is just that we write in atomic units, so we do not put those in. But if you want to calculate actual energy, we will have to incorporate all those once again. Okay, last term, what does it become? Numerator becomes z, denominator becomes r12. So, this is your Hamiltonian for helium atom in atomic units. Hamiltonian is half del 1 square minus half del 2 square minus z by r1 minus z by r2 plus z by r12. Okay. Remember atomic units. So, now I will start from this Hamiltonian and we will try to develop a perturbation theoretical treatment for the ground state of helium atom. If you want to do perturbation theoretical treatment, what is the first thing we need? We need the 0th order or unperturbed Hamiltonian. What would that be? That would be the sum of the 1 electron Hamiltonian, right. I do not understand this. Why have I not written it in atomic units? I do not believe I did that after saying all that. Anyway, let us go ahead. So, this here is the 0th order Hamiltonian, okay. And what is z square by 4 pi epsilon 0 r12, or in atomic units z by r12, that is the first order correction to Hamiltonian. What would the unperturbed wave function be? Unperturbed wave function would be the product of psi 1s of r1 and psi 1s of r2. That means, see, we are still using orbital approximation sort of, right. We are keeping the electrons in their own orbitals. So, electron number 1 is in 1s orbital, electron number 2 is in the other 2s orbital, other 1s orbital. These two are written in terms of r1 and r2, the two position vectors of the 2 electrons. This is my 0th order wave function. What do I need to do? I need to know also the 0th order energy. What would that be? This one is written in atomic units. Sorry for not writing the Hamiltonian atomic units here, but I hope this is not very difficult for you to understand. The 0th the uncorrected energy will be simply the sums of the 2 unperturbed energies of the 2 electrons. So, minus z square by 2 minus z square by 2 in atomic units gives me minus z square atomic units. Okay. I will just give you the result for the first order correction to energy, and just believe me when I say it is 58Z. It is not really worked out in any of these books that we are consulting, but pointers are provided on how to work this out in problem number 6 of chapter 8 of Macquarie's quantum chemistry book, right. If you work out that problem, you will arrive at this expression for the first order correction to energy to be 5Z by 8. What is total energy then? Total energy is minus z square plus 58Z, okay. That turns out to be minus 11 by 4Z, okay. There is a minus sign here that I missed, I am sorry. So, or I have to write E0 minus E first. So, that turns out to be minus 2.75 atomic units, which is 74.83 electron volt. Is that good or is that bad? Actually it is not all that good. So, let me now show you another compendium of results. Remember, when we had completely neglected inter-electron repulsion, the energy that we got in atomic units was minus 4. Okay. Here we at least we get minus 2.75. First order perturbation theory calculation gives us minus 2.75 atomic units. If we increase, if we do second order perturbation theory treatment, then the energy we get is minus 2.91 atomic unit. If we keep on going, then I will just show you the 13th order perturbation theory result. This is by Shear and Knight, published in 1963. Here we get, and now this see what I was talking about, you have to go to a lot of decimal places if you want to work with atomic units. We get minus 2.9037243. What is the experimental value? Minus 2.9033. So, the difference between the experimental value and the calculation involving a 13th order perturbation is in the 4th decimal place. Okay. Not bad. So, using perturbation theory you can actually get pretty close to the experimentally observed value, and see your variation the upper limit theorem applies here as well, right. We are not crossing it. Minus 2.90372 whatever is still more than minus 2.9033. So, that is what we get by using perturbation theory for our helium atom ground state. Next, what we want to do is we want to use variational method and see what we get, and as we said we have to discuss some more topics before we can get there. But one thing that I want to say here is that this is actually the beginning and not the end. Once we are done with this discussion of variation method, we will embark upon what is called the Hartree-Fock method using self-consistent fields to achieve a better value of the energy, okay. And we will see what that means, but what it will involve is where we had stopped the last module at. Remember, we had said that we should use a wave function that is a linear combination of orthonormal eigenfunctions of the Hamiltonian. Hamiltonian means Hamiltonian of the exactly solvable system if there is one, and then we do not work with those functions as such, but we build in some variational parameter in the functions themselves, not only coefficients. So, the coefficients are variational parameters, functions themselves also contain variational parameter, that gives us greater flexibility. So, it becomes again a numerical problem, right, and that would require algorithms, that would require quantum chemistry, and essentially what you would want to do there is you would want to minimize the energy with respect to each of the parameters. If you remember a few modules ago I had very sketchily talked about this, and we will talk about that once again later on. But Hartree-Fock actually enables us to handle larger systems. You do not want to stop at helium, and even for helium we need a 13th order perturbation theoretical calculation. So, what is going to happen for benzene, right? we want to talk about benzene, right, and nowadays people talk about much larger aromatic molecules, bigger molecules, so on and so forth. How do we handle those? In fact, I remember a very senior quantum chemist once told me that for him quantum mechanics begins after Hartree-Fock. So, for us in this course, let us at least go up to Hartree-Fock, and then later on when we talk maybe in some other more advanced quantum chemistry course, we can learn about more contemporary methods. Here we will at least provide the state of the art, a glimpse of state of the art later on. But we have made a good beginning. Today we have discussed what kind of results we get and what kind of improvement we get in the perturbation theoretical treatment of ground state of helium as we increase the order of perturbation. Coming up next is the variation method for helium atom.